Module 1, Laplace Transforms. Contents 1.1, Definition of Laplace Transform. 1.2, Laplace Transform of Elementary Functions. 1.3, Properties of Laplace Transforms. 1.4, Laplace Transform of Periodic Function. 1.5, Unit Step Function or Heaviside Function. 1.6, Inverse Laplace Transforms. 1.61, Computation of the inverse of e power of minus as f bar of s. 1.62, Inverse transform by completing the square. 1.63, Inverse transform by the method of partial functions. 1.64, Inverse transform of logarithmic and inverse functions. 1.7, Convolution. 1.71, Convolution theorem. 1.8, Solution of linear differential equations using Laplace transforms. Initial value problems. Many physical problems, when analyzed, assumes the form of an ordinary differential equation subjected to a set of initial conditions or boundary conditions. Such problems are referred to as initial value problems and boundary value problems, respectively. Laplace transforms serves as a very useful tool in solving these problems without actually finding the general solution of the differential equation by various known methods. The application of Laplace transforms is highly significant in engineering problems associated with electric circuits. 1.1, Definition of Laplace transform. If f of t means function of t is independent variable, function of t is dependent variable, is a real valued function defined for all t value greater than or equal to 0, means positive integers. Then the Laplace transform of f of t denoted by Laplace transform of f of t is defined by L f of t equal to integral of t equal to 0 to infinity e power of minus st f of t into dt, provided the integral exists. On integration of the indefinite integral. In integral, there are two types. One is definite integral and another one is indefinite integral. Indefinite integral means limits are not given in the integral. Integrally, no limits. So then that integral we call it as indefinite integral. We will be having a function of s and t. When this is evaluated between the limits t equal to 0 and t equal to infinity, we will be left with a function of s only, and we shall denote it by f bar of s, where s is a parameter, real or complex. It means both real and imaginary. Thus, Laplace transform of f of t equal to f bar of s. Equivalently, we can express this in the form L inverse of f bar of s equal to f of t. Here, Laplace transform of f of t equal to f bar of s. This L is shifted to right side. So, we'll get L inverse. And this L inverse, we call it as inverse Laplace transform. Inverse Laplace transform of f bar of s equal to f of t. Note, Since linearity property holds good for an integral, we can obviously infer that Laplace transform of C1 f1 of t plus or minus C2 f2 of t equal to this C1 and C2 are constant. Take outside C1, take this side C1 into Laplace transform of f1 of t plus or minus C2 Laplace transform of f2 of t. Here C1 and C2 are constants. Laplace transform of discontinuous functions from the basic definition. Working procedure for problems. Step 1. Here f of t is composed of different functions in different sub-intervals of 0 to infinity. Suppose f of t is when t vary from 0 to a, that time f of t is f1 of t. When t vary from a to b, that time output f of t will be f2 of t. When t is greater than b, otherwise b to infinity, so that time output f of t will be f3 of t. Then we consider the basic definition of Laplace transform of f of t, that is Laplace transform of f of t equal to integral of 0 to infinity e power of minus st f of t into dt. Step 2. By taking into account the intervals involved in the given f of t, we express the integral in the equivalent form by using a property of definite integrals. Therefore, Laplace transform of f of t equal to first interval is 0 to a, integral of 0 to a e power of minus st f of t dt plus when t vary from a to b, so integral of a to b e power of minus st f of t dt plus third interval means when t vary from b to infinity, otherwise greater than b, that time e power of minus st f of t dt. So this is for step number 2. Step 3. We substitute the relevant f of t as in the data. Now Laplace transform of f of t equal to integral of 0 to a e power of minus st f1 of t. When t vary from 0 to a, that time f of t is f1 of t dt plus second interval is integral of a to b e power of minus st, output f of t is f2 of t dt plus when t vary from b to infinity, otherwise greater than b, so means integral of b to infinity e power of minus st, so that time output f of t will be f3 of t dt. Step 4. We evaluate the integrals to obtain Laplace transform of f of t as a function of s. Note, if f of t is a polynomial in t, then we have to write integral of e power of minus st f of t dt as integral of f of t e power of minus st dt and use Bernoulli's generalized rule of integration by parts as follows. Integral of uv dt equal to first function is u, second function is v. So take first function as it is. Next, apply the integral for second function, integral of second function, integral of v into dt minus take first function as a differentiation. First function apply the first order derivative. Take first order derivative for this first function u dash and again apply the integration for second function, integral of v into dt, double integration. Next alternate sign, first time positive, second next time negative, next time positive. So first function ಗೆ ಒಂದ್ಸಲ ಡಿಫರೆನ್ಷಿಯೇಟ್ ಮಾಡಿದ್ವಲ್ಲ, again take second order derivative. Next apply the triple integral, minus alternating sign and so on, up to where ಫಸ್ಟ್ ಫಂಕ್ಷನ್ ಕಾನ್ಸ್ಟೆಂಟ್ ಆಗೋ ತನಕ ಹೀಗೆ ಡಿಫ್ರೆನ್ಷಿಯೇಟ್ ಮಾಡ್ತಾ ಹೋಗಬೇಕು. ಅಪ್ಲೈ ದಿ ಡಿಫ್ರೆನ್ಷಿಯೇಷನ್ ಆ್ಯಂಡ್ ಇಂಟಗ್ರೇಷನ್ ಅಪ್ ಟು ವೇರ್ ಅಂದರೆ ಫಸ್ಟ್ ಫಂಕ್ಷನ್ ಡಿಫ್ರೆನ್ಷಿಯೇಟ್ ಮಾಡಿದ್ರೆ ಕಾನ್ಸ್ಟೆಂಟ್ ಬರೋ ತನಕ. ಆಫ್ಟರ್ ಕಾನ್ಸ್ಟೆಂಟ್ ಆಯ್ತಲ್ಲ, ನೆಕ್ಸ್ಟ್ ಏನಾಗುತ್ತೆ, ಅಗೇನ್ ಡಿಫ್ರೆನ್ಷಿಯೇಷನ್ ಆಫ್ ಕಾನ್ಸ್ಟೆಂಟ್ ಬಿಕಮ್ಸ್ ಝೀರೋ. ಸೊ ಅಲ್ಲಿಗೆ ಸ್ಟಾಪ್ ಮಾಡಬೇಕು, ಕಾನ್ಸ್ಟೆಂಟ್ ಬರೋ ತನಕ ಡಿಫ್ರೆನ್ಷಿಯೇಟ್ ಮಾಡಬೇಕು ಆ್ಯಂಡ್ ಅಪ್ಲೈ ದಿ ಇಂಟಗ್ರೇಷನ್ ಸೆಕೆಂಡ್ ಫಂಕ್ಷನಿಗೆ. Next, illustrative examples. Example number 1. Find Laplace transform of f of t, where f of t equal to, when t vary from 0 to 4, the time output is t. When t greater than 4, the time output is 5. First, write down the Laplace transform of. Laplace transform of f of t equal to integral of 0 to infinity e power of minus st f of t into dt. Next, apply the ಲಿಮಿಟ್ಸ್ ಆರ್ ಇಂಟಗ್ರೇಷನ್ ಇಂಟರ್ವಲ್ಸ್ನ ಅಪ್ಲೈ ಮಾಡಬೇಕು. ಎಲ್ ಎಚ್ ಎಸ್ ಆ್ಯಸ್ ಇಟ್ ಈಸ್ ಈಕ್ವಲ್ ಟು ಫಸ್ಟ್ ಇಂಟರ್ವಲ್ ಇಸ್ 0 to 4 e power of minus st f of t dt. Next interval is greater than 4, so integral of 4 to infinity e power of minus st f of t into dt. Using the relevant f of t in the integrals we have, so LHS as it is, Laplace transform of f of t equal to first integral of 0 to 4 e power of minus st, so that time f of t is t, so t into dt plus integral of 4 to infinity e power of minus st, so that time f of t will be 5, so put f of t value is 5 dt. Next, Laplace transform of f of t equal to integral of 0 to 4. Here f of t is polynomial. Interchange the functions. First function t ಅಂತ ತಗೊಳ್ಳಿ, ಸೆಕೆಂಡ್ ಫಂಕ್ಷನಿಗೆ e power of minus st dt plus here 5 is constant, take outside 5 integral of 4 to infinity e power of minus st dt. Next, using Bernoulli's generalized rule for the first term in RHS. This is RHS. This one is the first term. So in this first term, integration by parts ಗೆ Bernoulli's generalized rule apply ಮಾಡಬೇಕು. So Laplace transform of f of t equal to, first function is t as it is ಹಾಗೆ ಬರೀರಿ. Second function ಗೆ apply the integration for second function. Integral of e power of minus st is e power of minus st divided by minus s. Next, alternate sign negative ಆಗುತ್ತೆ. Take the differentiation for first functionಿಗೆ differentiation apply ಮಾಡಬೇಕು. t ಗೆ differentiate ಮಾಡಿದರೆ 1 ಆಗುತ್ತೆ. ನೆಕ್ಸ್ಟ್ e power of minus st ಇದೆಯಲ್ಲ, ಅಗೇನ್ ಇನ್ನೊಮ್ಮೆ ಇಂಟಗ್ರೇಷನ್ ಮಾಡಿ. Again apply the integration for this one. E power of minus st ಗೆ integration ಮಾಡಿದರೆ e power of minus st divided by minus s, already minus s here, minus s into minus s ಅಂತ ಹೇಳಿದ್ರೆ, so that is minus s whole square. Then again apply the differentiation for this, so differentiation of constant is 0, so stop here only. Next, apply the limits 0 to 4 ಅಂತ ಬರೀರಿ. Write down the limits here 0 to 4. Next, plus 5. Integral of e power of minus st is e power of minus st divided by minus s. Then write down the limits 4 to infinity. Next, minus 1 by s take outside. So first apply the upper limit t ಗೆ. For t, is upper limit is 4 e power of minus 4s, and lower limit t is 0, 0 into e power of 0. E power of 0 is 1, but t value is 0, 0 into anything is 0, minus s whole square is plus s square. Take this side common outside, minus 1 by s square. Apply the upper limit here, e power of minus 4s minus of lower limit e power of 0 is 1. Plus into minus is minus 5 by s. So next t ಗೆ ಲಿಮಿಟ್ಸ್ ಅಪ್ಲೈ ಮಾಡಿ e power of infinity, e power of minus infinity, e power of minus s into infinity is e power of minus infinity, e power of minus infinity is 0. So because e power of infinity is 2.71 something answer to the power of infinity, so 2.71 etc. to the power of infinity becomes infinity. E power of minus infinity is reciprocal of the infinity, e power of infinity. So e power of infinity value is infinity. Any value by infinity is 0. So therefore e power of minus infinity value is 0. Put 0 here. Next apply the lower limit minus e power of minus 4s. Next multiply these two, minus 4 by s into e power of minus 4s. Next multiply these minus into this one is minus 1 by s square into e power of minus 4s, minus minus plus 1 by s square into 1 is 1 by s square. Next minus minus plus 5 by s into e power of minus 4s. So here minus 4 by s and plus 5 by s, take LCM, will get 1 by s. So 1 by s into e power of minus 4s. Next here take 1 by s square as common. First minus of e power of minus 4s, this is plus 1. Next here e power of minus 4s by s plus 1 by s square into 1 minus e power of minus 4s. Next second example, find Laplace transform of f of t if f of t equal to 0 when t vary from 0 to 1. F of t is t when t vary from 1 to 2. F of t is 0 when t greater than infinity. First write down the Laplace transformer formula. Laplace transform of f of t equal to integral of 0 to infinity e power of minus st f of t into dt. Next apply the limits. Laplace transform of f of t equal to integral of 0 to 1. First interval is 0 to 1 e power of minus st f of t into dt, plus second interval is 1 to 2 e power of minus st f of t dt, plus third interval is greater than 2, otherwise 2 to infinity e power of minus st f of t dt. On substituting for f of t, we have only one integral in the RHS because first term f of t answer is 0, second term f of t will be 0. So first and third term cancel out. So consider only second term. So Laplace transform of f of t equal to integral of 1 to 2 e power of minus st f of t value is t dt. Next here polynomial of f of t is t. So interchange the places. First function t, second function is e power of minus st dt. Applying Bernoulli's rule, Laplace transform of f of t equal to first function t as it is. Second function, apply the integration for second function, e power of minus st divided by minus s, minus take the differentiation for first function. So differentiation of t is 1 and integration of e power of minus st is e power of minus st divided by minus s. Minus s into minus s is s square plus s square. So write down the limits here, t equal to 1 to 2. Next minus 1 by s take outside. Apply the upper limit t equal to 2, 2 into e power of minus 2s minus lower limit is 1. So 1 into e power of minus s. Next minus 1 by s square take outside. Next apply the limits. E power of minus 2s minus lower limit is e power of minus s. Next Laplace transform of f of t equal to, this minus is multiplied on this. So 1 by s into minus is plus e power of minus s, minus into plus is minus 2 e power of minus 2s. Next illi minus and take outside. So minus plus e power of minus is plus minus e power of minus 2s.